Everyone, it's August 14th. Alright, yesterday night was terrible. Man, that problem really got us. So today we have something easier. Oh, hold on. This is from yesterday. Yeah, so I have to go read this person's solution and then try to fix mine. It's all very, very complicated because they changed it. They changed the test case and thing, and then it just got really, really tough. Oh, then this person responded. I might post mine. Yeah. I'll post mine. This is just some good solution. Anyway, let's go for this one. This is an easy one, but I actually remember this is not that easy, right? It's not that easy. It's Roman to integer. Oh, it's Roman to integer. That's why it's easy. If it's integer to Roman, that's actually a little bit more difficult. Okay. That's 20. That's 7. Yeah, the 4 is IV, right? X can be before L and C makes 40 and 90. C can be placed before D and M makes 400 and 900. Okay, so just a couple rule passing, right? We're gonna pass the rule. So the difficult rule is always in front. IV, like the case is IV, IX. Oh, and like IIV. Wait, is that IIV? No. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So the case is IV, IX. X can be put before XL, XC, CD, and CM. These are edge cases, right? So as you scan through, if you find a pattern like that, then you need to treat it differently. Like in this case, right? We say M by itself. M can have, what's M? M is 1,000. Okay, so we see a M, right? If it's not a pattern, then it must be 1 by 1 from big to small. So M, okay, that's 1,000. Then we see a C. But when we see a C, we don't immediately go for 100. We have to see if it's a CM, right? If it's a CM, it is. So that is going to be 900. And X, again, X is, what's X? X is 10. So that's a 10. But it's XC, right? XC. And then IV. Oh, it's just loaded with these edge cases. So basically, we have, if we encounter a V, that must be V by itself. If we encounter things that's not IXC, anything that's not IXC is just going to be by itself. If anything is IXC, we have to check the next one. Basically, that's what this one is. All right, so we're gonna say we have rules. Okay, let's do the rules. I is 1. Oh, V is 5. X is 10. L is 50. C is 100. D is 500. M is 1000. And IV, that is 4. IX, that is 9. XL, that's 40. XC, that is 90. And CD, that is 400. And CM, which is 900. Okay, so these are our rules. And now we're going to parse, and the result equal to 0, right? I'm going to parse, which is say for, I don't know, probably shouldn't 4. Probably should probably should I it here. 0, right? While I is smaller than line S, we say if Si is in V, Vx, right? L, C, D, M. If you see any of these, then rest plus equal to rules Si. Done. Done deal. Nothing else. That means it's something else, right? If it's something else, which is the I, X, and C, then we need to check the second one, right? Then we need to see if then we say else. If it's I plus 1. If I is smaller than len, actually, well, let's do this. N equals to len S to N. If it's smaller than N, if this plus 1 is smaller than N, and Si plus 1 is in VLC. Oh. No. Aleph Si to I plus 1. No, I to I plus 1. It's just I. It's actually I plus 2. Alright? It's in IV, IX, XL, XC, CD, CM. Right? If this, then rest plus equal to rules. I want to call it again. Yeah, that's fine. Actually, I think this one shall be the first to check. If this in this, else rest plus equal to rules Si. And then this I plus equal 1. This one I and a plus equal 2. Sounds fair? Then return rest. Well, in this case, I'll do like this. Okay, we can test this. Shall be 3 LV that shall be 58. That is 1994. 1994. good. Does this make any sense? No, this doesn't make any sense. It should be a valid Roman integer. It has to be big to small. Alright, let's just do this. If it's wrong, then it's wrong. It's tired to get into the nitty-gritty. So, that's right. Done this. This is the third time, right? Yeah, that's the third time. How did we solve it in the first time, 2018? That's when everything started. This is actually a good beginner problem. I agree. 13. Early. So, 3,009. Ah, yeah. Yeah, for sure. Oh, wow. It's actually the same idea. It's actually the same idea, except you don't have to do all this. You can just put it in. Yeah, back then I didn't know better. Okay, so I'm done with this. I'm gonna respond to this person. Show my solution yesterday. We have a solution. God, is that solution with 5? Okay, so I think I'm going to try to use this. Right, this is his solution. So how I will do it, I do it this way. Let's see if we can merge the two solutions together. This is his solution, right? Oh, Jesus, what the heck are you doing, man? Q, we have this. I say I can remove this. I don't need this. And then the dist actually can just become an int. And this is fine. Right, so while Q, we can do that. Actually, the Q, we also don't need this. We only need this. So we do this. If V equals break. No, we don't need this. Don't need this. For this in this, if would not in dist first encounter. Alright. If would not in dist first encounter, then if it's first encounter, we definitely will say Q append W and dist W shall equal to 1 plus dist V, because it's always 1. The first encounter is always the smallest, right? And after that, this is just to check if it's first encounter. Okay. Now we're gonna say if 1 plus dist V is equal to, so W, we do this, right? And then we say if the dist W is the immediate, right? Then pred this dot append V. So basically they're just saying that whether W is the immediate right? The closest immediate offspring of V, because we will say W's parent is V. So this is to check whether W's parent is V. Is they differ by only one step. So I would go for this, and to test its correctness, all I need to do is go copy his solution, go here, and then swap in my implementation and see if it works. Basically, that's how it is. So I'm going to get rid of all this. Get this in. All right. We're going to run test case. And so test case good. We have 3 huge things that we can try. So of course, is it the first one? Yeah, I just think as long as you do it back to front, you should be fine. The key is always back to front. You need to do it back to front, and that's the most important thing. Back to front. So I'm adding these 3 test cases. Yeah, it is good. So with that, then I'm confident that this one is working. Okay. Wait, hold on. Hold on. Cancel. I reply to this. Oh, this goes up. So the BFS of the BFS portion using your here's your coding pattern. Let's preview this. Using dist to check first encounter, right? First encounter of a word. Also, I've made some changes to how the dist. I've simplified. I've also simplified some of the logic. That should be good. It's reverse order. That does make sense. You should go that way. I've already encountered it. So if you have encountered it, then the job is not to put it again, because you already know it's going to be in the queue, right? So another job is just to see if it's going to be a parent. Yeah. Because dist was saved always. Maybe I should add a few more. Yeah, should be fine. Yeah, so what might happen is if W occurs early on, right? And now I can go to W again, from V to W again. And that is true parent, actually I should say. If W's true parent. Earliest parent. We only consider earliest parent because we want shortest path. We want earliest because how should I express this? Yeah, I think it should be, that should be good enough. Okay, well, I think that's good. It works. Now it's just records the shortest distance from any word to begin word. That should be it. Okay, now let's try to do this. I have an idea. Okay, I have an idea that I can try. No, we're not done yet, man. We ain't done yet. This is 90. Okay, what do we want? We want to minimum number of obstacles. So the ideal is we're going to go from the end, going back, because this was deterministic. The number of obstacles that needs to be removed to get here is 0. Okay, and then it is deterministic that to reach here, we have to reach here and here, right? So if this is 0, and this one doesn't have any obstacle, then this one will be 0 as well, right? And this one has an obstacle, so this one will be 1, right? And then from here, we find the direct parent, right? It's going to be this and this, right? And then what we're going to do is we will just update the value. I think it's going to be a cube, and I'm going to use a grid, a DP grid, okay? And we start from here, then we get these, right? And then everything will be, let's say, -1. So that means it's not being visited. And when we hit stuff, we say here, if it's not being visited, actually, hold on. Even if it's not being visited, it should still I will assign, right? Because I say this can come here. So I say I'll push this in and I will assign a value to this. And I'll push this in and I'll assign a value to this. So I will assign a value. So every time I visit, the value is already being set, right? If this value has already been set, then when you visit this, your goal is just to try to find the next one, right? You're trying to find the next one. You're trying to find the next one, and then you're going to pass your value to this, which means you're going to update. And we want the smallest. So actually everything is set to the maximum. So we go here, and everything will visit, but we can use a set. So the next visit will not have duplicates. Let's try. So what we're saying is, okay, we actually need math. 10 to the 5th. Yeah, I probably shouldn't use this. Hold on. Can we use this? Probably shouldn't. No, I don't think we should. I'm gonna get a DP table. And line grid 0. Okay, DP equals to math.inf times n. It's for this in range m. Okay. Then we say q will equal to n minus 1, n minus 1. Right? That's the q. And then we say, well, q. And then dp n minus 1. N minus 1 is 0. Hold on. That is going to be grid n minus 1. N minus 1. It could be 0. It could be 1. Okay, so while q. Temp is this. Actually, temp is going to be a set. Then we first just say for ij in q, right? Then we're going to look around the things that it can go. So we have 4 directions, right? Everyone has 4 directions. But honestly, for these, all I can do is up and left, right? Like for this one, because this, like everything is a square. So we go well, bottom right corner, right? We'll check this one, we'll check the one. These are the first thing. And then when you are here, you're coming from here, right? You never check this. So you can only go this and this. You can only go this and this. So the next will just be these 3. So we will never go down. So we can only check up and left, right? We'll just only check up and left. And then we'll just say, so for ij, and then we say for di dj, right, in 2, up and left. So up will be this 0. Left will be this, right? So I say ni and j equals I plus di, j plus dj. If zero smaller equal to ni smaller than m and 0 smaller equal to nj smaller equal to n, so that's the one that we can do. Then we will say dp ni nj shall equal to minimum dp ni nj and dp ij plus grid ij ing. Right, so this just means we want to keep this one as the minimum, right? And then, because this is the where you're going to go to, right? So if at dpij I will take a certain number of the minimum number of removals to reach, then you will definitely take the minimum of me plus whether you are open or not. So we do that and I give the minimum. And I'm going to go through blah blah blah, go through all of them, and then once we're done, temp.add an ing. Like, simple. I don't have to worry. It's just a tuple. And then it's a set, so there'll be no duplicates. And then we just do this, blah, 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 do this. Once we're done, we say q equals temp. So q become a set, which is perfectly fine. And then blah, 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 once we're done, we just return dp 0, 0. Okay, let's see if this one works. Feels like too simple, so I am not very confident. We'll see. Yeah, if it fails, that's fine. It's a difficult question. My standard for a difficult question is actually very, very, very lenient because I know my capability. So it's never too much of an issue. Oh, I have issue. The second one shall be 0. How do we come up to 1? Yeah, some problem, huh? For row in dp, let's print row. Let's take a look. So we have 0, 0, 0, 0. These are 0. These two are 1, right? So when we hit this, I think the propagation, so this one will hit this and this, right? And then this one will hit this and this. This one will hit this and this. So this one become a 1 because this is a 1. We're going to go 4 directions. Go 4 directions. Hold on, let me see. If we go 4 directions, so when we hit here, 4 directions, so over here we go 4 directions. But if this one has been visited before, if it has changed its value, then we need to redo it. Oh, now we have the complexity. So first of all, I do think, yeah, this do have to go 4 directions. It's okay. So 1, 0, 0, 1. Ode. And we say if ode is not equal to the yang, then this one needs to be reprocessed. Okay, so we're basically just reprocessing it. Now, performance-wise, what's the hit? How long is it going to take for it to stabilize? That is a good question. I do not know, but try. We have to try anyway. Judging. Worst case scenario, we just time out. And if it time out, we just calm down and then think about a better solution. Time out. So this is correct, which is important. We can define a solution 0, and we say TLE. This could be giving us some confidence. It's 51 out of 54. So it's not too bad. It's not too bad. But definitely this one's taking a toll, right? This one's taking a toll. The reprocessing is taking a toll. I mean, now I need a new idea. Oh, I have hints. You want to try hints? Maybe later. Alright, okay, let's look at the hints. Alright, what hint do we have? Model the grid as a graph. Where cells are nodes and edges are between adjacent cells. Edges to cells with obstacles have a cost of 1, and all edges have a cost of 0. Oh my god. I think I need more practice with this type of problem. This is not the first time. It's not the first time that a grid problem can be solved with graph. So what it's saying is then the cost from this to this will be 1. The cost from this to this will be 2, right? Because there's 2. Okay, let's draw out. Alright, so this cost is 1, and this cost is 2. This is 1, this is 0, right? And this is cost is 1, cost is 2, cost 2, this is cost 2, cost 1, cost is 2, this cost is 2, and this cost is 1. Okay, so this is the graph version. And we want to find a path to the end such that the cost is 0, right? The cost is 0 by removing as few boxes as possible. And then we can take however we want. Right, hold on. If this cost is 1, if you reach, no, I think these costs are 1. This is not cost 2. It's just 1. And if you go into an empty, there's no cost. If you go into something that is a block, then it's a cost 1. So I'm going to rewrite the cost. So this 1 is 1. This is 1. That's 1. This is 1. This is 1. 1. 1. And these are zeros. As you move into an empty cell, the cost is 0. Okay? So this is 0. This is 0. 0 and then 0. There's a 1, 1, 1, 1, 1, 1. There's all ones. Okay, so now the question is to go from source to destination. Right, what is the, oh yeah, the cost is always going to be 1, right? It's either 1 or 0. So I just want to find a path with the least penalty, the least weight. When we talk about Dijkstra, come on, is this Dijkstra? The shortest path with weight. This is exactly what we're looking for. The shortest weight. Wait. That's Dijkstra, right? Oh my god, we're gonna code Dijkstra again. Yeah, I think this is Dijkstra. Dijkstra is to find the path with the minimum weight. And this is to find a path with a minimum weight. Dread. I wish one day I can say, oh, it's Dijkstra. I know how to code it. Well, use the first hint and try Dijkstra. I wish I can say, oh yeah, I know how to code Dijkstra. I do know how to code Dijkstra, but gotta think. So Dijkstra is you start and then you put the next into a priority queue, and then the smallest will come out, and it will go to all its next one, and when I go to all its next one, we'll update. Alright, we'll update its weight and push it into, and every time the pop out will be the smallest one, and we will reach the end. Then when we reach the end, we want to see the cumulative weight of the path. Okay, so I need a heap. And what? Heap is going to be this, which is actually heap is going to be 0, 0, right? And we need your weights. I'm going to use this one. Okay. And weights 0, 0 is going to be 0. Which is a start. It's 0. Okay. And we know all the neighbors, and we know, do we know its weight? The weight of the edge, right? The cumulative weight to reach that is the weight plus the edge, right? The weight plus the edge. And we are just going to and I'm going to have a visited. I'm going to have a visited. It's going to be a set. Okay. So I think it's a while heap. We'll pop out. Go to the next. And each time we go to the next, we will have the new weight. Right, we will update the new weight, and if it's smaller, we update and then push again. If it's not smaller, then we don't do it. Okay, so it's a while heap, right? ij equals heap_q.heap_pop. Okay. And then what? Oh, we need to have its weight. Do we need its weight? If we keep track, we don't need its weight. I know it's waiting here. So, but you have to have, right? So we say W, that's the weight. Okay. Then for, I can use this code. Okay. So for blah blah blah, this blah blah blah. So that's the next one. Oh, and ninj not in visited, and visited dot add inj. It's been visited. Okay. Now, if there's not in visited, then I can say, right, the current weight equal to weight plus grid and inj, right? It's either a 0 edge or a 1 edge. And then we say if current weight is smaller than weights and inj, then weights and inj will equal to current weight, and heap q dot heap push heap. I'm going to push current weight and inj into it because it's smaller. I want to push into it, right? So we're done. Check the next one, check the next one, check the next one, and that's it. We're going to go back up. Pop the next one is the smallest, and we do this. Now, we also need to have a cumulative weight, 0, okay? So every time we pop out, because we will always reach the first, so we can actually say cumulative weight plus equal to W, right? And then we say if I equal to n minus 1, no, m minus 1, and j equals to n minus 1, then we're going to break. We have reached the end. We have reached the end. Wait, is that cumulative plus equals? What is W? W is to reach this. What's the total weight? So I don't even have to have this. I don't have to have this. It's just when this, when I break out, W is the thing. So I think I can just return W. M is not defined. Of course it's not defined because I didn't even do it. Here. Takes exactly one argument. Heap pop. I did not put heap inside. They pass. Okay, let's try this. Lord. Oh, look at that. We might have it. We might have it. Oh, yes. Well, did take a hint, but I bet the second hint is Dijkstra. Yep. It's Dijkstra. All right, two things. First, I am able to code Dijkstra from scratch. So that is definitely a plus. Okay, very happy. Secondly, grid problem is not the first grid problem that I have encountered, which can be easily solved by turning into a graph. And there are a lot of tools in graph that we can use, and this is certainly a very prime example of how this can help us, right? This definitely helps us tremendously. It's a good problem. Is it difficult? The first one requires, if you do this one often enough, you'll kind of get a hint. So what we're trying to do, going backwards, that we have to refresh the thing. So that's why it's not the best idea. But it's brilliant, right? If you think about it, it's brilliant. Basically, it is like how many things you will have encountered. Yeah. Why would you think about Dijkstra? Well, you think about Dijkstra, not really think about Dijkstra. You think about, I want to find a path, right? So I want to find a path from top left to lower right such that it encounters the minimum number of obstacles. That's the gist of the problem. We want to find a path like that. But it's difficult to find if you just traverse, like you do DFS. It's really difficult to find because you can go like this, right? It's like, how do I know when should I turn? No, it's never like that. So you say, okay, basically I want to find a path with a minimal number of obstacles. A path with a minimum something. A path with minimum something. A path with, that sounds like Dijkstra, because Dijkstra is to find a path with minimum weight or maximum weight. Doesn't really matter, right? You say, okay, does this mean I can use Dijkstra for this? And you start thinking, the number of obstacles we encounter, just like if we say a path entering a cell that contains obstacle will be 1, cost is 1, otherwise cost is 0. That exactly reflects how Dijkstra can be constructed. Boom, that's how you solve it. And the actual coding time is not that much. It's not that much. So, two things, right? Two things. The good, I can code up Dijkstra from scratch. The not so good. I won't say bad, but just not so good. The intuition to turn a grid path problem to a graph problem still needs improvement. The key is to realize that we can consider a path going into a cell with obstacle as a path of weight 1, and whereas a path going into an empty cell as a path of weight 0. Then the problem becomes to find a path with minimum weight from top left to bottom right. This is exactly what Dijkstra does. I think that's all my login, right? That's the Dijkstra complexity. I got a bit nervous, right? It just constantly rotating, spinning, never giving me a result. Got scared. Anyway. Multi-set to, oh shoot, I can do even better. Dijkstra. Multi-set deck. Do I select the newest? Not hot. Most voted. What's 01 BFS? Minesweeper. Like, seriously, what's 01 BFS? I think this person has the same idea as me, which is the initial solution. Multiple entries of the same cell. Yeah, gets updated, exactly. Oh, when the distance gets updated, you need to... That's the intuition. Lazy Dijkstra. If I give 4 directions, I will go with graph. Oh, my bad. Is that O? It's Bellman Ford. Is this Bellman Ford? Ooh. Let's see. So we have this. Oh, is this Python? Why you do things like this? Seriously, why you do things like this? I have a deck. It's Bellman Ford. So we have the distance, okay, and yeah, I seem to remember this Bellman Ford. They always put the smallest at the front. If you encounter something that has not been visited before, which is here, a new node, and we say if it's 1, yeah, then the distance, that's distance as well. That must be the distance. And we put it at the back. Otherwise, if it's this, we'll put it, so we give preference if it's an empty. Interesting. Yeah, this is a heap queue. I can return here. That's true. Oh, wow. This is interesting. Holy crap. Oh, you don't even need visited. Oh, brilliant. Brilliant, brilliant. Visited is not needed because the weights. Oh, crap. That's not 0. I think we just got lucky. Wait, hold on. I think we just got lucky. Oh, invalid test case. No, we're not getting lucky. It's required. Yeah, that's not necessary. Whew, thought we got lucky. No, we did not. We pop. So we don't need visited because everything's this, and we just say if this and w plus grid ninj is smaller than grid ninj. The current is definitely better than, just say this equals w plus grid. We have to, yeah, I have to say this all the time. NJ. Oh, we can use weights in NJ. I think that is the more typical Dijkstra. But I got it wrong. What? Hey! What the hell? If this and this. Oh, my bad. This is weights. Yeah, this is the more canonical. Update. No need to use a visited set because we can because whether to add a node to the heap is entirely dependent on whether the new weight is smaller, right, than the old weight. Yeah, so this is, and distance. Interesting. No, I think this is the distance. No, the number moved to reach. Yes, I think this is true. I think that's Bellman Ford. They have like a Bellman Ford. Somebody explain a Bellman Ford. Oh, is that the? I don't know. Is that the 01 BFS? Yep, that's the 01 BFS. What the hell is the 01 BFS? Alright, I think I'm gonna end right here because I need to search something called 01 BFS. Never heard of it. Alright, that'll be it. See you guys tomorrow. Adios.